Well, hi. Welcome to the end of year Spacetime AMA. I'm Matt O'Dowd, as you may know, and I'm very excited to be doing this. Uh, it is the end of 2021, which makes me think maybe there's something wrong with the Earth's gravitational field. Time seems to be passing more quickly. Actually, it's been quite a long time since we did our last AMA. It was back in the beginning of the pandemic, the first lockdown in New York City. Um, and so we decided that it was time for me to have the opportunity to make a fool of myself in front of how many are we? Well, perhaps thousands of viewers. Normally, you see me on a green screen reading from a teleprompter, something which I'd written only the past day. But there are no teleprompters here. There are only your questions. We have a set of questions that we collected from the community channel on the YouTube page, which I'm going to address vaguely in order of how popular they were, and also somewhat in order of my capacity to answer them. But I'll do my best to address your questions there in the chat as time allows. We're going to spend about 30 minutes. So, without further ado, I will get started. First question, let's start by making this all about me. Because Country of Austin asks, what is my background in education and physics, and how did I end up as the host of the show? Well, the background's straightforward. I did undergraduate in Melbourne, Australia, studying physics. And then I went on to a PhD in astrophysics. That was in Baltimore, of all places, the Space Telescope Science Institute, which back then was in charge of operating the still quite shiny Hubble Space Telescope. Did that for a few years, back and forth with Australia, ended up in New York City, Columbia University, and finally managed to score a real job for the first time in my life at City University of New York, Lehman College. That's my CV. I do some research as well as the show, and I may talk about that a little bit. But the other part of the question is, how did I end up as the host of PBS Spacetime? Well, if any of you have the energy to scroll all the way down to the bottom of our videos page on PBS Spacetime, you'll find of order 20 videos by another guy. The incredible Gabe Perez-Giz, who is, as you would find out by watching those, quite a savant, was the original host of the show. Of course, Gabe is a New Yorker, and we knew each other. We were friends, and Gabe moved on to, let's say, well, better, more interesting, certainly different things. Let's say I did him a favor by stepping up. Those were huge shoes to fill. Especially if you watch his episodes on general relativity, you'll see how much of a genius Gabe really is. I shook things up. I strongly encourage you not to watch the first of my videos that followed Gabe, although you can watch the one where we had a lightsaber fight to win control of the show. Long story short, every single astronomer in the world was inspired by Carl Sagan and thinks that the duty of an astronomer is to bring space to the people. Just like them, I wanted to tell people about the universe. Let's move on. Before I wanted to tell people about the universe, I wanted to study the universe. So the question by Eddie Scapazza is, what am I currently researching? To follow on to that, so my work is, broadly extragalactic astrophysics. I am am very much focused right now on gravitational lensing. So using the fact that massive bodies bend the paths of light according to Einstein's theory of general relativity. So when you look out there, you see, nearby you see stars, okay, twinkling. Those stars are roughly where they appear to be. But the further you look, the more likely you are to find things that are not where they appear to be. And the coolest of those are cases where you have a very distant object whose light traveling through Einstein's universe of curved space-time follow curvy paths, and sometimes those curvy paths are deflected back towards each other by an intervening massive object, a galaxy, for example, and reach us. And so we can see the distant objects through two paths through space. I like to look at quasars that way, quasars being gigantic black holes in the process of consuming material from their surrounding galaxy. And so this gravitational lensing allows us to, in a sense, tack an additional galaxy-sized lens onto our telescope so we can study those distant objects in ways that we could never do with a telescope built by mere humans. And so currently I'm working on building machine learning algorithms to try to understand the complex variations in the light of distant quasars due to this gravitational lensing effect. All of this in preparation for the LSST survey, which is going to begin operation on the Vera Rubin telescope in only a couple of years' time. Okay, and you can be sure that I will update you as soon as we start to get reasonable results. All right, so there are so many good questions. Let me jump into some science. We can come back to personal stuff if you like later on, but there are such good science questions. I'm going to start with Milind Upathye. I apologize for my pronunciation. And the question is, when an electron emits a photon and another particle, let's say a proton, absorbs it, what causes the particles to be attracted? Okay, I'm actually slightly misquoting this question, so forgive me, Milind, but I think this is the question that I certainly want to answer, and hopefully you want to hear. Okay, so we have this strange description of the forces in quantum mechanics, in particular in quantum field theory, where two particles which are either attracted to each other or repelled from each other are so influenced by the exchange of virtual particles, virtual bosons. In the case of, say, an electron and a proton, we draw these little diagrams where the electron and the proton are moving together, and a little virtual photon wiggles between them, causing the particles to be drawn together, or in the case of two electrons, to be drawn apart. And you might think that in that viewpoint, if you have two particles that are coming together, and one particle essentially throws a ball of force at the other particle, how is it that those two particles could actually be attracted, given that the photon is expected to exchange momentum with the proton, and that photon is moving in a particular direction? So this is a common misunderstanding, and the real trick to understanding this question is to understand that virtual particles are not real. Rather, they're a mathematical tool that's used to represent the behavior of the quantum field. And it's a whole nother topic. Why is it that assuming that virtual particles are real actually gives us the right answer in quantum field theory? And we do have an episode on that topic, but I'm not sure we answered this question, because this is really a great one. How is it that exchanging a particle between 2 points can cause those points to come together? Surely the momentum transfer should push them apart. And the answer to that is that, well, there are a few ways of looking at it, and there are ways to answer this that do away with virtual particles altogether. But even though virtual particles aren't real, it is possible to answer this question assuming they are, or in the context of virtual particles. And that answer goes something like this. So when you calculate the interaction between two particles, whether they're repelled or attracted, using Feynman diagrams, okay, so what you do is you add over all the possible ways that virtual photons could be exchanged between the real particles, the electron and the proton. And in doing so, you sum over all possible momenta that those exchange particles could have. In a sense, every way those particles could interact, they do interact, and sort of the weighted sum of all of those interactions gives you the interaction that actually happens, or the probability distribution of that interaction. So in that context, every virtual particle that you're adding, that you're calculating in that process, has a specific, perfectly defined momentum. And as we know from the Heisenberg uncertainty principle, if a particle has perfectly defined momentum, it has perfectly undefined position. So it, in a sense, occupies all space. In a sense, let's say the proton is causing a vibration in the entire electromagnetic field through all space. And so what that means is that the proton can excite virtual photons that are able to reach the electron coming from any direction. Okay, the photon doesn't really travel a distinct path between the two particles. It can hit the second particle coming from any direction, and that means that it can transfer momentum from any direction. And when you sum the momentum transfer in the case of particles with opposite charge, you have more momentum transferred in the direction that drives them together. And in the case where they are like charges, there's more momentum driving them apart. But as with any story that we tell about the mathematics of physics, we can't take these stories too seriously. And we can't set, these physical interpretations, we always need to take with a grain of salt. There are other valid ways to explain this one. But that's enough for now. I am inspired by this question, and I think we probably need to do a proper episode on it. Okay, so I want to move to a nice astrophysics question, because we don't talk about astrophysics enough, I think, me supposedly being one and all. Okay, so Stefania asks about cepheid variables. Okay, how are they possibly so regular? Where do they come from? Do they become supernovae? And something, thanks, lol, from Italy. So Stefania, lol to you too. And for those who aren't familiar, cepheid variables are some pretty crazy stars that they're giant stars, so many, many times larger than our sun, and they pulsate. They pulsate in brightness and they pulsate in size. They kind of sort of breathe over periods of time from a few days to several weeks, or even a few months in time. And the crazy thing about cepheid variables is that the period of pulsation is very tightly related to the amount of energy that cepheid variable's giving off, what we call its luminosity. And that's a super powerful tool, because if you notice a cepheid variable out there in a distant galaxy, all you need to do is time its pulsation rate. And if you time its pulsation rate, you immediately know what its intrinsic luminosity, how bright that star really is. Using your telescope to measure how much the distance has dimmed that star, you can actually figure out the distance to that star in the same way that you could, say, figure out the distance to a car that's down the highway based on the brightness of its headlights. And of course, Edwin Hubble used cepheid variables to find out that the universe is expanding, blah, blah. I think we have an episode on that. But that wasn't the question. The question is, how are they possibly so regular, and where do they come from? Which I don't think is addressed much in the pop science literature. So it's a pretty cool phenomenon, and kind of straightforward, actually. So these are stars that are approaching the ends of their lives. In some ways, they're at the ends of their lives. They've finished burning hydrogen in their cores, and they've expanded to giant stars. And the core has undergone what we call the helium flash. So they're now fusing helium into carbon in their core, but they're still gigantic. And these stars go through these phases where the outer layers are fairly opaque. Okay, so the outer layers, when the star is in the dim and compact phase, tends to trap energy, traps light inside the star. Okay, and so for that reason, they're dimmer. And what happens is that the insides of the star starts heating up. Okay, the energy builds up, and as it does so, the star expands. The pressure increases, the star expands, and at some point, the outer regions become diffuse enough that all of that light escapes. Okay, and so they radiate brightly as the light starts to escape, and they reach a certain maximum size where they're basically, the outer layers become close enough to transparent, and so they cool down. If the energy is escaping, they cool down and they start to shrink again. And as they shrink, opacity increases, and so you get this regular process. And it's just regular because stars are simple beasts in a sense. As far as astrophysical objects go. Okay, they're nice and round, and they reach the same opacity, and it takes the same amount of time to do it each time. Okay, and so they pulse like that for quite a while, and then eventually explode as supernovae if they're big enough. Not all cepheids are quite big enough, but many of them are big enough that at some point that helium fusion core will start to fuse the other things, and they'll do all sorts of crazy stuff that ends in a gigantic explosion. But that's a story for another time. Okay. One more science question, and then I'm going to try to hit the I'll try to hit the chat. This is just me, by the way, guys, so bear with me while I manage everything. Normally I have so much more people reading things for me. So this is a really good one. This is Morgan get your name right. Morgan 242242 always thought that instead of many worlds as a way to interpret quantum mechanics, why don't we interpret it as many times, where branching is just movement in a second time dimension? Has there been any thought on interpreting it that way, and would it make a difference? Well, Morgan 242242, that is a unique way to interpret it. I haven't heard it quite said that way before. So the idea of many worlds, I've talked about it plenty, but the idea is that every time, the evolving wave function in the quantum world sort of makes a decision in the sense of a measurement being made and, say, an electron having to choose one position or another position. Anytime we get what in the Copenhagen interpretation of quantum mechanics we'd call the wave function collapse, there is no real collapse. Not one decision is made about the location of the electron, but rather the worlds split, and all possible locations that the electron could end up are realized. Okay, so we have this infinite or possibly infinite branching of the timeline. And so to think of this as many times rather than many worlds, it's a nice thought. I would just say that we don't actually need multiple dimensions of time to do this. We can think of many timelines, but we don't need separate dimensions of time. If you think about branching paths, okay, so say branching paths through a forest, each extra path isn't necessarily an extra dimension of space. So in order to have branching paths. So each individual path you can think of as one-dimensional. For there to be branching paths, you don't need many dimensions, you just need two dimensions. Okay, so you need one additional dimension for the paths to branch into. And if there are trees in the way, or if you're, separated in the quantum multiverse, then you don't see the other paths anymore, even though you're only separated by a single dimension. In the case of the many worlds interpretation, the extra dimension is actually there, and it's more of a degree of freedom. But what is the difference between a degree of freedom and a dimension isn't clear. There is something inside each wave function, inside each sort of quantum iota of existence that that can change, and that thing is the phase of the wave function. Okay, so it's exactly how, for example, the peaks and the troughs of that wave function line up with respect to some other part of the wave function. And the idea being that if there is what we call coherence between different parts of the wave function, then those different parts of the wave function can interact with each other. But if they are, as we say, decohered, or their phase, relative phase relationship is scrambled, then they get lost. It's like the paths diverge and can't come back. And so in a sense, we do have that, that dimension, a really degree of freedom. In this case, it would be the phase of the wave function. But it's still a really cool way to think about it, and I'm going to steal that. Okay, I'm going to quickly scan the chat here. There's a couple of other questions I'd like to get to, but this could be a good time. We put this on slow, but it's gone so fast. Does loop quantum gravity attempt to explain dark energy? I think so. I think loop quantum gravity can calculate the vacuum expectation value, which would give us dark energy. I don't know if it agrees with what is observed. Pasius Achilles asks, is my beer painted? Yes, this is actually normally a luxurious brown. I paint on these little white parts just to gain some amount of credibility in academia. These are, of course, fake glasses. Otherwise, no one takes me seriously. Have I read the recent paper? So, Charles, have I read the recent paper concerning the warp bubble, the one by the DARPA team? So now I have to answer that question because I read it out. I possibly should have avoided this one, but so I've skimmed the paper. I admit I haven't read it in detail. So that's my answer. All right. So let me tell you a little bit about this. So for those of you who haven't caught this, this is the notorious Professor Sonny White, who originally was of EagleWorks Labs, which was a NASA affiliated facility. Okay, I wouldn't exactly say that it was part of NASA, but it was NASA affiliated. And these are the guys who have been trying to make the EM drive work. Okay, so they thought they had positive results for the EM drive. That's this inertialess drive. It's a copper container where you bounce microwaves around, and it manages to accelerate without ejecting fuel. That's been solidly debunked at this point. But they've also been playing around with trying to experiment with the Alcubierre warp field. Okay, so this is one of the earliest episodes we did, if anyone wants to go back. But the idea of the Alcubierre warp field is that you have this distribution, this particular distribution of energy that, and as we know from general relativity, the presence of a distribution of energy can warp the fabric of space. And so Alcubierre, Miguel Alcubierre, Mexican physicist, found this metric in a solution to Einstein's equations that produces a field which is capable of traveling faster than light. Now, the only problem with this solution is that it required a type of energy that doesn't exist, and that is a negative energy density. So as far as we know, energy can only be positive um, in almost any circumstance at any rate. So that seemed to be a bit of a downer. But the hypothesis that Professor White and team are working on is that there is this one case where we sort of have something like negative energy, and that is in the Casimir experiment. And this experiment, you have two conducting plates that are excruciatingly close together, so close together that there are, back to virtual particles, there are virtual particles, parts of the quantum vacuum that sort of are excluded from the plates because of their wavelengths. They're excluded from between the plates, and so you lower the energy density below the level of the quantum vacuum, and that causes the plates to pull together. Okay, and this has been a verified result. It's certainly it's an incredibly difficult experiment, but it has been conducted. And so this is supposedly a type of negative energy. So maybe we can make a warp field with Casimir energy. And so the headlines were that physicists had accidentally discovered a warp drive. So White and team had been trying to do this using, as far as I can tell, capacitors. Okay, and a capacitor is conducting plates that are close together and sending a bunch of electric charge through it. I'm sure that it was more advanced than that. Apparently, this was in a separate project to, for other reasons, study different Casimir plate configurations, and in the process, they found some kind of energy distribution that vaguely resembled the distribution in the Alcubierre warp field. And then they did a bunch of calculations using, as far as I can tell, a somewhat fringe offshoot of quantum mechanics that's based on Bohm's pilot wave theory, Bohm-de Broglie pilot wave theory. And I admit I didn't follow that too closely. But the first thing to note is that these were simulations. Okay, this experiment hasn't been actually conducted. Okay, so in their computer simulations, they found that this thing vaguely represented resembled the Alcubierre warp field. It's not clear to me how closely it resembled the Alcubierre warp field. I'm pretty sure that this was largely hype. A big part of the problem, even if it was an exact solution, a big part of the problem is that there's no way to make Casimir energy without having these, by comparison, really massive conducting plates and that tiny sliver of negative energy between them. And so, what you really need to consider is what is the net energy in the region where you're trying to generate the warp field. And as far as I can tell, it's impossible to create a negative energy density without having a much higher level of positive energy density. So that's a bummer. I personally wouldn't place much stock in it. But maybe we can end this on an up note. Well, there was one question, and that question was, let's see. I've got them all here, guys. Stick with me. Well, I can't remember who asked it, but it was essentially, what is the one idea that I'm convinced is true, the one hypothesis that I'm convinced is true that is not proven and that most scientists don't accept? So the first thing that came to my mind when I read that question, and it may not properly answer the question, is simply the idea that, okay, faster than light travel is not possible, but interstellar travel is possible, and we'll one day achieve it. I think that there's nothing fundamentally stopping us from expanding and becoming an interstellar species. But my gut instinct is that if it's possible, and if the galaxy is full of life, if life is common, then per the Fermi paradox, we should have been visited many times, and it should be very apparent that aliens exist. And so how do I reconcile my instinct that we haven't found aliens yet, and my instinct that interstellar travel is possible? And it's simply that I think humanity is early to the party in the Milky Way. Okay, and it's like the thing that for some reason seems likely to me, but I can't adequately put a pin in why I think that must be the case, except some very circumstantial babbling that I won't subject you to right now, but future episodes. There was a really good one from, let's see, how about this one? From Laz, the creator. If I held the purse strings to an unlimited science budget, what wild experiments or projects would I greenlight? So I have to start by, I can't be entirely selfish. I'll talk about my selfish answers, but first up, if I could just fund anything, I think we have to start by just getting fusion taken care of once and for all. Seriously, here's an analogy. Not doing fusion, not investing a significant fraction of humanity's resource into just getting that taken care of, I see as like the species level equivalent of not wanting to get out of a warm bed to use the bathroom. We know we have to do it eventually. We'll be so much happier once it's done. So we might as well just bite the bullet and do it. And the risk in both cases is rising water levels and general embarrassment. There are probably some other humanitarian and environmental projects that I would greenlight, but if I'm forced to use the money for things that purely excite my curiosity, we really have to find out what is up with dark energy. Dark matter is cool, but figuring out what dark energy really is, it feels like it's the thing that's going to bust open the most doors to the next levels of our understanding in physics. And I guess the other thing that we've been sadly lacking in, sadly ignoring, is understanding the fundamentals of quantum mechanics, so fundamental interpretations of quantum mechanics. For decades and decades, it was career suicide for a physicist to even want to study fundamentals and the interpretations of quantum mechanics, and that's only stopped being the case in the past couple of decades. But there are so many enormous open questions there, and we talk about physics being stuck because string theory can't make progress and our giant particle colliders can't find new particles. We still don't know what quantum mechanics means, and there's relatively minimal work in trying to understand, what the wave function is, why the square of the wave function is a probability distribution, many worlds versus Copenhagen. All of this stuff, I think, is where I would put money, and it doesn't take a lot of money. You just got to buy some physicists enough blackboards and coffee, and it'll get done. All right. So guys, I think how are we doing for time? Well, we're over time. So we're going to end with, this one. Malimuk asks, hey Matt, what is the threshold at which a cup becomes a bucket? So let me add that to my list of things that I would research if I had unlimited funds. In fact, I did some research after reading that question. I Googled it. All of those other questions, of course, I answered off the top of my head, but this one I had to Google. And I learned that, in fact, we do have some work going on. In fact, apparently PewDiePie first covered this very important topic, but it then had a very popular thread on Reddit. So Malimuk, welcome from either PewDiePie or Reddit. My own answer, um, you know, I'm not a black and white kind of guy. I think there are shades of gray. I think bucketness or cupness is relative. Uh, Kenny Houghton asks, "Is the bucket spinning or not spinning?" Referencing the classic Isaac Newton thought experiment. But Tricky actually gives us an answer, and this is probably right. The answer is a pint. So there you go, guys. It's been a delight talking with you. Um, I'm just gonna watch your comments for a second. Time is an illusion. I like that. ALL. How is the electron not a force carrier? I saw in all caps, guys. We're going to steal all of these for episode ideas. This is why we really did this. We just wanted to tap your brains. It's been fun, guys. We'll do this again before too long. We won't leave it as long. I'm delighted to stumble over questions in humiliation for your entertainment anytime. And I will see you real soon. Have a wonderful holidays, and I will at some point find a way to come up with better ways to end my episodes with the words space time.